look at electromagnetism, right? We are saying it. This is a discovery. A current carrying conductor will produce magnetic field. This is a fact that we need to know, right? Now, to determine the direction of that magnetic field in the current carrying conductor, you use what we call right-hand rule. But in a few, I will show you another way of doing that right-hand rule, in case it's difficult. Okay, another way of getting the magnetic field. So if you have a straight conductor, this is a straight conductor shown here. This is a straight conductor. And if the direction of the current is going up, so we're having the current is going up like this. This is the direction of the current. Then you can use what we call a right-hand rule. So basically, a right-hand rule, you take your hand, the thumb will represent the direction in which the current is going, to represent the direction of the current, and then you curl your fingers around the conducting wire. So the curled fingers will represent the direction of the magnetic field, will indicate the direction of the magnetic field. So yeah, so just like this is indicated in this diagram here. So we see this is the direction of the magnetic field. It's going around like this, like this, like this. And this direction is called anti-clockwise. It's called anti-clockwise. Right. So it is also indicated here that the thumb, your thumb, it will point in the direction in which the current is going. Your thumb points in the direction of the current, so it's pointing up. And then your fingers will be curled around, and the curled fingers will indicate the direction of the magnetic field, the direction in which the magnetic field is going. So sometimes we look at the top view of the conductor. So this is our conductor, and then when you have our conductor like this, we look at the top view of that conductor. So this is the top view of the conductor here. This is the top view of our conductor. This is the top view of the conductor. Even here, this is the top view of the conductor. Now, if the current is going out like this, or the direction of the current is represented by this dot here, to show that the current is going out like this is going out like this up, then we should use a dot, right? Then in this case, this top view is indicated here like this. This is the top view, to indicate that the current is going down like into the page like this, in like this, is going in. To show that the current is going in, we use a cross like this. So the word dot is related to the word out. If I say dot and out, so check dot and out, they are rhyming. So when you see a dot, it means the current is going out of the page. And then if you see a cross, so I look at crossing, the word crossing. Crossing means in. We're going into the page then. Right. we also have to be able to determine, to use right hand rule to determine the direction of the current there. Sorry, the direction of the magnetic field, right? So here in this top view where we have got dot, and then here where you have got cross, if you want to determine the direction of magnetic field, right, since the dot represents the current that is going out, the dot is representing the current that is going out, the cross is representing the current going in to the page, right? But we now want to determine the direction of the current. So to determine the direction of the current, the direction of the magnetic field, you use right hand rule. Although you use right hand rule, it might be difficult. So I came up with a strategy of saying don't cross. I say don't cross. I just say don't cross. So if I say don't cross, don't cross. Now the emphasis is here on the don't, is on the N. This is the N, right? So if I look at the N like this, do you see that if in red there is dot, D-O-T, dot. Now I'm going to use this N to determine the direction of the current, of the magnetic field in the dot, when I have a dot. So at the end of the N, I write an arrow like this. I write an arrow like this, and then it will show me the direction. So what I do is this. I have a dot, so I draw an N like this, then arrow, I draw an arrow. Right, so to draw the magnetic field lines, these are the magnetic field lines, right? Then I have to indicate the direction of those magnetic field lines. So on the right, I'm going up, just like it's indicating I'm going up. So I indicate up then. Then this side I'm going down. This is down, so I'm going down this side, like this. So the direction of the magnetic field is going like this. And this is an anti-clockwise. This is an anti-clockwise direction, right? Because the way the anti, you see, the way the anti has got anti-clockwise, has got the word N. Anti-clockwise. It has got the word what? N, meaning here when I determine direction using N, it is an anti-clockwise direction. Alright, the direction is called anti-clockwise. And then the N helps you to show the direction. Then the name of the direction comes from the word anti, where also N is part of that, of the anti. Just to remind yourself, right? Then to determine the direction of magnetic field, here I draw magnetic field lines first, going like this. They go around like this. Now this is a cross, so with cross I focus on the S like this. Then at the end of the S I write the arrow, right? So I write, this is the S. The S has got an arrow, So meaning I must write an arrow there, going this at the bottom. At the top, I must draw an arrow like this. Then I remove the S there. Do you see the direction of magnetic field now? It's going like this. And this direction is called what? Clockwise direction. It's called the clockwise direction. So check. If I indicate here, I wrote this word. I say, anti, don't cross into clockwise. If you remember this phrase, then you will understand what we are talking about. So we are saying if I have a dot, okay, if I have a dot, I use N to determine direction. And that direction, the name of the direction will be called anti-clockwise, because also the anti has got the what? The N. See? Right. So this one is about having a dot. This word is about having the dot. The dot where the dot represents the current that is going out of the page. So when you have current going out of the page, the direction of magnetic field is anti-clockwise. Out, anti. And then going into the page, then that is clockwise. Yes, that is clockwise. But now, to indicate on the diagram when you draw, and this is how we indicate, we use the N this side, and then this side I use S to indicate the direction of magnetic field. So where I have cross, okay, it means the current is going into the page and the direction is going to be clockwise. And to indicate it on the diagram, I follow the cross. Cross has got the letter S. So I write arrow like that. Then that will show me the direction in which magnetic field lines are moving around the, what do we call around the conductor. So here magnetic field lines are going this way, and then yeah, that is on the in front. Sorry, they're not going that way. In front, going like this. This is the front part. This is the front. This is the front. Right. And then here, magnetic field lines are going this way. Direction there, this way, like this. This is the front. This is the front. And this is the front there. What is eventually, because eventually here, this arrow is going to continue like this. It's going to continue going like this, because from here like this, I go like this. You see, we go like this. So here we go like this at the back there. Right. So even the diagram indicates that this is a dot. The direction of magnetic field lines are going like that. If I show dot with a dot, I show what? This is the N, right? Arrow. So I draw what? I draw, you see? Then I draw this side on the left. So on the left, you draw arrow down, on the right, arrow up, like that. So that's why the arrows are going up like this on the right. Then on the left, they will go down, down, down. Then here I use S. So you can see that this is an S. arrow there, arrow there. So it shows that indeed going down, when you have a cross, this is a cross, going down like that, and then on this side on the left is going up, right? And this is what? This is clockwise. This is clockwise, and this is anti-clockwise direction. I said anti has got what? The word anti has got what? N. So it shows the N, the one that is determined using N is anti-clockwise direction. So again we say anti, don't cross into clockwise. Anti is like you're saying your ant should not cross into clockwise. Anyway, yeah, just a way of reminding yourself, you know. So how will you draw the magnetic field lines around this? The direction of magnetic field lines around this. So you draw what? Direction of magnetic field line for cross. Okay, I start with the magnetic field lines. I draw this is the magnetic field line. Then I have to indicate the direction thereof. For a cross, the emphasis is on the S. Cross the S. Right. So this is the S with its direction. So then now I follow the arrow. You can say I follow the arrow the way it is, which means it's still going this way, right? Then there we are. If you want, there we are, like this. Then you can draw your magnetic field lines. It's just that this is at the corner. I'm not able to really do the right there. Draw a circle. Okay, it should be. Then for a dot, said we use N. Said what? Don't. So we're going up this side. We are going up. This side we're going down. So going down this side. Okay, and we're going up this side. And then you wrap the end so you can see the direction of the magnetic field. And this is an anti-clockwise because the word anti has the N again, just to remind you anyway, right? If we look at this multiple choice question there, which of the following sketches below represent the correct magnetic field pattern around a straight carrying conductor? Obviously, this is wrong, right? Then we check if there is a dot, okay? If there is a dot, remember I say don't. Yes. So I use N there. If I use N there, going like this, okay, it means on the left it should go down, on the right it should go up. It should go up like this, right? Then if I rub the N now, I remove it. Obviously this is wrong. This sketch is wrong because when you have a dot, it should go in this direction. It should go anti-clockwise. it should be moving anti-clockwise like that. So it's wrong. So by default, the answer will be B. But to confirm that, we said this is a cross. We see a cross there. We see a cross. When you see a cross, you write the word cross. And then the emphasis is on the S. The S there. You can write your S like this. Arrow, arrow. Right, so if I write S like this, the arrow should go this way. And the other arrow should go this way. Right, so on the top, the arrow should go, should be going exactly the way it's indicated. At the bottom, it should go this way. So yes, indeed, this one is correct, because it corresponds with what we just did. Okay, so correct option is B. Right, let's look at this question here. A square induction coil with a side length 3 centimeters and 400 windings is placed perpendicularly in a uniform magnetic field, then rotated through the angle of 45 degrees in 0.08 seconds. The EMF that is induced is that state Faraday's law. So you should be able to state Faraday's law. So Faraday's law, it says the magnitude of the induced EMF is directly proportional to the rate of change in magnetic flux linkage with the conductor, just like the formula states. E is equals to negative N delta phi over T. But if we only focus on this when we state Faraday's law. Focus on that. We say the magnitude of the EMF induced. The magnitude of the EMF induced across the end of a conductor is directly proportional to the rate of change in magnetic flux linkage. Rate of change in magnetic flux linkage, they are referring to this. This is the rate of, so EMF is directly proportional to the rate of change in magnetic flux linkage. That is Faraday's law. Right, they say calculate the change in magnetic flux. Remember, change in magnetic flux, we know change in magnetic flux to be final flux minus initial flux. Right, but I cannot use this formula because I don't have the value of B. Which is magnetic field strength. But what do I have? I have EMF, and let me check the number of turns. A square induction coil. Okay, so it is a coil that has got one loop, because they are talking about, sorry, it doesn't have one loop. The number of turns is N, I have it, is 400. Then the time I have it's 0.08. So we have everything. We just have to calculate the change in magnetic flux. So we're using this formula there. All right. So when we do substitution here, you say, okay, the EMF is 7. You write this formula, then you substitute 7 for EMF, negative 400, then change in magnetic flux is what we're looking for, divided by 0,08. So if you do your maths, you get negative 1.4. 4 times 10 to the power negative 3 Webers. So basically, when we solved the maths here, we cross-multiplied. Cross this multiplied by that, and then we divided by negative 400 both sides. Then, so to continue, here determine the magnitude of the magnetic field. Right, we can see that they are rotating. It's from perpendicular then to 45. It means these are changes in our angles, right? This change in angles will cause the change in magnetic flux. From placing it perpendicularly to now placing it at an angle will cause the change in magnetic flux. So now we say, so we say, okay, for initial flux, this is equals to B A area cos theta. Then we don't have the initial, we don't have the magnetic flux, magnetic field we don't have. Where it's unknown. Then the area of a square is equals to side square. But our side is 3 centimeters, so that 3 divided by 100, it becomes 0,03. So it's 0,03. The cos. Initially, it was placed perpendicular, but is this a normal perpendicular? I don't see the word exists, and I don't see the word normal. Either normal or exists. I don't see any of these two. So which means this is not the normal perpendicular. And if it is not the normal perpendicular, the angle theta is equals to what? 0 degrees there. And B is unknown. Then for the final flux, this is equals to, we don't have the value of B, but the area is still the same, 0.03 u square cos of, the angle is now they say they rotate it through the angle of 45. No, 45. Now, having this two, I can now apply the formula of change in magnetic flux. So change in magnetic flux. I know change in magnetic flux is final minus initial. So our final, it is B 0.03 squared cos 45 minus B 0.03 squared cos 0. So this is the initial, this is the final. Then we are going to solve for the value of B then. So if you do the right maths, this is the answer. You will definitely get here as the answer. Get there. So B is unknown. So the value of B there is this. It's 5,31 Teslas.